All right, thank you. And thanks to all the organizers for this opportunity to present this work. The same title it's the same title as the paper that I wrote with my supervisor, Marcel Vonk in Amsterdam. And what we did is revisited the study of the computation of instantons in quantum mechanics. So I think many as you know, this is a by now a pretty old topic. Several textbooks have been written about this. But I want to show you today that there are some new things that we've been able to do. So here's a small overview of people who worked on this topic. This is in no way an exhaustive list. It's way more people, but these are especially some papers that I liked very much and that I read. Foremost, if we go back to the 70s and 80s, there were already people who computed these instantons for one-dimensional quantum mechanical oscillators. I think one of the most well-known ones is Saint-Justin, who came up with this instanton calculus procedure. And subsequently also people like André Voros and Delabert Dillinger-Pham and also Alvarez and Casares produced all sorts of ways of computing instantons. And all these approaches essentially lead to something that we call a quantization condition, which allows us to quantize the energy spectrum of the Schrödinger equation. And the nice thing, of course, about studying these instantons of quantum mechanics is also that we can study resurgence, because resurgence was, of course, conceived in the world of ODEs. But we would like to see if these aspects of resurgence, like for instance non-perturbative decoding, this notion that instantons are actually hidden in the large order behavior of perturbative coefficients, we would like to see if these things are also true for physical systems. And one of the easiest ones, and the first example that people studied was, of course, quantum mechanics. This was actually implicitly already done by people like Bender and Wu, who studied the large order growth of the quartic oscillator, but also again people like Saint-Justin, Brezin, Parisi, Zensura, and more recently also Gerald and Mithat Unzal studied these instantons with resurgence and showed that these instanton corrections that you can compute often come with ambiguities, and those ambiguities can be cancelled against the ambiguities that you find when you resum the perturbative series and also the higher order instanton series. So what I want to show you today is what we did is improve on this by computing, again, instanton corrections, but what we show is that you can actually, besides just recursively computing instantons, you can compute them in a single sweep. And that gives you a closed form transseries expression which includes all instantons. And I'll show you that this transseries expression is constructed from two elementary building blocks, which are two formal power series. And once you have, say, 100 coefficients of those two formal power series, you can compute now the first 100 fluctuations around any saddle point which you like. You don't have to recursively compute them one by one. So that's one of the things I want to show you. And just to note, lots of tricks and techniques that we used in doing this, and also part of the motivation for working on this problem is due to a series of papers that came from the Geneva group by people like Codecido, G. Gu, Marcos Marinho, Ricardo Schiappa. So the Geneva group plus collaborators. So they studied the connection between quantum mechanics and topological strings. And recently in this Gu-Marinho paper, they found a trend series, and actually our initial motivation was to study how that trend series and its boundary conditions could be fixed. And we found out that quantum mechanics is a nice way to do that. But I will not discuss that side of the story that much. But it's important to note that we use some similar techniques and stuff. So what I want to show you today is really do this a bit lecture style. So I'm going to really, show some details. I will set up the problem. So we'll start with the Schrödinger equation. I will introduce something called quantum periods. I will show you how we can derive these or formulate quantization conditions. And then I'll show you how you can use these to compute instantons. And once we have, formulated this trend series, which includes all the instantons, we're going to study its resurgence using alien calculus. And if time permits it, I will also dive into this thing that we propose in the paper, which is this trend series factorization. Because the model that we're going to study is a double wall potential, and as many people know, not all instanton saddles know about each other in this double wall potential. And it turns out that the full transseries structure can actually be factorized in the product of two structures that we call a minimal and a median transseries. But I will explain that later on. So let's start. We will start, as I promised, with the Schrödinger equation, which we all know and love. And what we're going to assume is, as I mentioned, a symmetric double well potential. And we'll take this one. Usually one introduces here an anharmonic coupling, G, and produces expansions in G. We will not do that. We will set G to 1 and work with expansions in H bar. So H bar will be our small parameter here. And of course, the object that we're going to study is the energy. And the way in which we do this is by starting with a WKB ansatz. I think everyone is familiar with this. So essentially we take this object. Oh, sorry, now I'm... All right, is this big enough? Maybe this is a bit small. All right, so this object here is a formal power series with coefficients depending on x. And this thing solves a Riccati equation. And I will use quite often here, it's a bit unclear, I apologize, a semicolon to distinguish the expansion variable h bar and the parameter which sits in the coefficients. So this is an h bar expansion with coefficients depending on x. And the nice thing about this Riccati equation is that you can compute P0 and then it allows you to compute P1 and then P2 and so forth. And the nice thing is that this leading piece, P0, it satisfies a particular equation. And for our quartic potential, you can see that this thing essentially is an elliptic curve. And so this thing we call the WKB curve. And to see this more graphically, let me draw the potential. So say that here we have the energy, and there will be here 4 so-called turning points where the energy and the potential are equal. And we can draw then in the complex x-plane these 4 turning points. And then we can draw these cycles. And usually one also draws Stokes lines, but for the purpose of this talk we won't need to do that. So these cycles I'm going to label gamma, gamma dual, and again gamma. Because due to the symmetry these are essentially the same. And if you consider this piece here, then you consider this as a differential 1 form and you can integrate along these cycles. And what you find then are what we call quantum periods. So the first quantum period I'm going to denote in this particular way. It's going to be integrating this quantum differential with respect to x along the non-trivial cycle gamma, and it produces yet another power series in h bar. Now in this case you find even powers of h bar. This is due to the fact that all the odd solutions or the odd quantum corrections to this Riccati equation or Riccati solution turn out to be total derivatives with respect to x. And so if you put them here in the integral, then they vanish. And it's just a convention, but usually one writes here 1 over 2 pi. And besides a quantum period, there's also going to be a dual quantum period, which carries a prefactor minus I, which again is a formal power series in even powers of h bar. So the minus I is also quite convenient because you will find that if h bar now is positive and real, you'll find that the quantum periods are positive and real. So that's kind of useful in this context. All right, so we've written down these quantum periods, and what I will show you in this is that these are going to be elementary to formulating these quantization conditions. But we are interested in E, and at this moment, E is nothing but essentially a modulus of our quantum curve. So we want to invert we want to change independent variables. So far we've been working with E and H bar as independent variables, but I want to switch to T and H bar. So I want to use the quantum period now as an independent variable. And so this is a formal power series with coefficients in E. And so we can invert it to produce a formal power series for E with coefficients depending on T. So if you just take this as an ansatz and plug it in here, you'll get the composition of two expansions in H bar. By imposing that one is the inverse of the other allows you to fix these coefficients if you know these. And these, of course, we can compute because these are the solutions of the Riccati equation integrated. So far, starting with the Schrödinger equation, we can compute this object. And we can plug it in here to get also a new dual quantum period, but now expressed in terms of T. So I apologize in advance. I'm going to abuse notation a little bit. But I will always write the argument. So you will always see when I'm talking about this guy and this guy. It's going to be mostly this guy. All right, so this is again a formal power series. All right, and so what I will show you now, or in a bit, is that these two formal power series are going to be the elementary ingredients of our full-fledged transseries. All right, so that concludes the first part. So, put here a 1. So let's now go to part 2. Before I continue, are there any questions so far? Sorry? Yeah. If E was complex, yeah, then they would become also complex because then these turning points would move into the complex plane. Yeah, and that would be different. So really, so the last thing I didn't catch. Yeah. Yeah. Yeah, so we pick these particular cycles in this way because it's very convenient, because we will always assume that they lie on the real axis, yeah. Yeah, we're assuming, good point. In fact, we will always assume that the energy lies between these 2 points. Indeed, you can draw in the complex E-plane, you can draw kind of like a circle, which is like a minimal chamber, right? If you stay in this zone, if you go out, you get this wall crossing phenomenon. We will not be considering this. We will assume E is real and to lie between these 2 lines. It's a good point. It's important to keep in mind. All right, so now I want to show you how to compute the energy, because so far we have an energy expansion in H bar depending on T, but so far this can be anything because we did not fix T in any way. And the way you do this is using a quantization condition. I will not derive them, but I will show more or less how they arise, the motivation behind them. And it will be very instructive to first consider what I would call a perturbative quantization condition. So imagine that we just zoom in on one of the wells, which locally looks like this. So there is this cycle T, which kind of determines the size and implicitly the height of the energy. So what we're going to do is we're going to take a wave function here. In fact, it's going to be a basis of wave function, because this thing, of course, you take a square root, so here you get a plus minus, so here you get a plus minus. So you have a basis of WKB solutions. One of them you require to decay here, and then you analytically continue it to the other side, and then you get some sort of connection formula. And what you want to do is you want to fine-tune this connection formula in such a way that now on the other side, the appropriate component again vanishes. because this enforces that the wave function is square integrable over the real line. Again, we're just looking at this locally without ignoring the fact that there are other wells. So if you do this game, you can compute this either by doing it the hard work, analytically continuing this thing in the complex plane with all the Stokes lines, or you use Vorow's Silverstone connection formula or uniform WKB. You will find eventually, in this case, a very simple relation. So this relation tells you that T is quantized. You can all see what the solution is. And so N here will be, let's write it here. It's a bit inconvenient. So N will be an integer, and in fact, consistency requires N to be a non-negative integer, because it's related to the question. If N, of course, is negative, the energy will lie below the barrier, and therefore you would not be able to derive this condition or connection formula in the first place. So this we can write in this particular way, and then we can plug this into our energy expansion, and for this particular case, we then find so these are the first two terms of the perturbative energy expansion. So this is a textbook computation. You recognize here, by the way, that this is, of course, the harmonic oscillator term. But because this thing is, of course, not perfectly quadratic, we're going to have some kind of corrections, perturbative corrections. This is h bar, sorry, nu. So instead of writing everywhere, powers of n plus 1/2, I replaced n plus 1/2 by nu. Sorry for my handwriting. So this is nu squared. Yeah, so this is a textbook exercise, and there's different ways, of course, to do this. But the nice thing about this approach now is that we can easily generalize this to the non-perturbative case, where we now have two wells. And now we will have to consider 3 cycles. And you can do the same, you can play the same game. So you take a wave function over here, you analytically continue it through the complex plane to the other side. You impose that the wave function, the appropriate components of the solution vanish on either side. And you find a new quantization condition. And it reads, if it looks like this. All right. So what do we see? We see on the right-hand side this exponentially suppressed term. Remember, the dual quantum period is positive and real. Note that this is a full-fledged h-bar expansion. So it's not just, so this is 1/2 h-bar. So if you expand this thing, h-bar corrections will drop down. And because this is exponentially small, you can also see that if we just briefly ignore this part, we retrieve our original perturbative quantization condition. What else do we see? We see here an epsilon. So this is called the parity. And it takes values +1 or -1. It's essentially a quantum number. So actually we're looking at 2 equations. One for symmetric wave functions and one for anti-symmetric wave functions. So there's going to be 2 quantum numbers in the end in the game. Those are going to be n and the parity epsilon. And then the most interesting thing that we see here is this ambiguity. And this is the same ambiguity that we're going to find in the end for the instanton corrections. And the nice thing now is that there is a way to pick one out, and that is by giving the imaginary component of h bar a small, or the imaginary part of h bar a very small component. So if you do that, for those of you who know exact WQB, you will know that there is here a saddle trajectory between the Stokes lines, and you kind of lift this degeneracy when you give this small phase. And this is we're gonna come back to this later on, because we'll see that there's also a natural resummation prescription associated to each of these. And that will allow us to identify one ambiguity in the trend series with one particular resummation prescription. All right, so this is what we call an exact quantization condition, and it will give us the energy trend series. All right, let me see. Yeah, so how does one solve this? Well, the classic way to do this is in a recursive manner. So what we do is we acknowledge that this t is going to be different from the perturbative one. So we're going to give this guy a hat. And what we're going to say is that this solution is almost the perturbative solution, but due to this extra piece, there's going to be some instanton corrections. So this is more or less our ansatz, and when you plug this in here, you can derive an equation for these non-perturbative small corrections that this new t obtains. And what we find is all right, so let me, yes. So this is t. Yeah. Yes, I will. All right. So this equation implicitly defines delta t. It tells us how it gets instanton corrections. And this will be the thing we kind of want to solve for delta t. Now note that here the dual period is evaluated again at t hat, which is t plus delta t. So solving this is kind of the challenge here. And the most straightforward way to do this is by a simple ansatz, by saying that delta t is going to be a sum over instanton corrections, where lambda now is again this dual period, but now evaluated at t and not t plus delta t. So this guy, I remind you, is assume very small. So we take this guy, we plug it in here, and we expand, and we let Mathematica do it for us. And then let me show you. And when you do that, you can plug this in the energy, as we did before in the perturbative case. So then we get that the trend series is this guy, and the result you can see over there. So these are the first three orders that you find. And you can see the ambiguities appearing. You can see that there's this epsilon dependence. In fact, you see that the epsilon dependence appears at the odd sectors. I'm cheating here a bit. The even sectors will also have an epsilon dependence, but it will be even powers of epsilon. And since epsilon is plus or minus 1, we can remove those. And you see also derivatives of the energy, so the perturbative energy, E, and this dual period. So every time it's this E. So this before quantizing, before plugging a value for t in. It's this E. Yeah, so we did not yet replace E with this guy. It's a good, yeah, this is a very subtle point. We kind of, we at the end, you want to, indeed, if you now want to get a physical value, you need to first, in this case, for instance, differentiate E with respect to t, and afterwards you plug in this value. But for now, we're going to use t as a formal variable. And there you see that E prime or T dual prime is really those formal power series differentiated with respect to this parameter T. And if you stare long enough at these equations, you will see that, you know, as you get further, you get, as you can see, a mess, but you can organize them in a very efficient way. By including this instanton transmonomial on the left-hand side, you find that here we had for the third instanton correction 7 terms, but actually you can regroup them in 3 by using some clever integral of a partial integration. And if you look even longer, you will notice that this seems to suggest this particular relation. So what I want to show you now is that this is that this relation turns out to hold. So this is the expression for the energy transseries. So I want to derive this thing, and I want to show you that we can also determine these coefficients u and m. And for that we use something called the Lagrange inversion formula. So that will be the third part now of the talk. Before I start, are there any questions? All right, I will use, let's see. Let's go over here. So I'm not going to go in full detail, but I kind of sketch what this formula is and what eventually the closed form expression is for these coefficients u and m. So the first thing we note is that this equation for delta t, which is given here by the log, we can do is we can insert here, and so yeah, it's a bit annoying. So what we can do here is we insert here counting like a bookkeeping parameter z, which counts the powers of z, count the powers of the instanton transmonomial, and this allows us to write delta t in the following way. So let me see. Yes, this particular way with coefficients rk, zk. And this thing we write as some sort of object which implicitly determines delta t. So delta t solves this equation, right? And these RKs will play a role because they will end up in the coefficients u and m. And now there is this Lagrange inversion trick. And it states that if I take some arbitrary, let's say, well-behaved function of delta t, which is analytic as delta t goes to 0, then we can write out a closed form. We can compute this object if delta t is determined by this equation. And it reads as follows. Let's see. Yeah. So at this point, you should think of this. So this is a phi, by the way, far phi. Sometimes it looks like a q. I apologize. So this is kind of like, you should think of this like a given equation proved by mathematicians. It's hard for me to give an intuition why this works. But one thing you can check, that if you put delta t equal to 1 in this case, you'll find that this guy, of course, is also 1. So here we just get 1 to the power m. You can take this derivative with respect to delta out, and you see that 1 over m factorial and then m derivatives is essentially, you know, computing the nth coefficient of the expansion with the variable set to 1. So that's unfortunately the best intuition I can give you for this formula. But the nice thing is that if we say now that this guy is our energy plus delta t due to this equation can be also expanded in terms of z. And so we can also expand this object in terms of z, and we can then compute En in terms of z, and what we find is that this guy then becomes, let's see, oh, I forgot one important thing, right? So this is how you extract the coefficient, right? The nth coefficient, you differentiate n times, divide by n factorial, and then you set, of course, the thing to 0. So that's the intuition, by the way. So here we then get, again, here the, in this case, dE dt, again, this object to the power. All right, so this is a sketch. I don't expect you to fully, be aware of all the intricacies that go into this formula, but the nice thing is that this guy we can now compute, and I'll show you the end result. What we find is that this thing is h bar times the sum of m goes from 0 to n minus 1. Then we find here 1 over n factorial, and then we find some Bell polynomials, and those are expressed in multiplied by h, the derivative with respect to t, to the power m, acting on the derivative of e, and then lambda to the power n over 2. So this is the formula I showed you there, and you see that this guy here, these are the coefficients u and m. So the, yeah, sorry, this, there's 1 factorial r1, 2 factorial r2, it's a r, yes, sorry, it's a small r. It's essentially, it's these guys here. So, so what's happening here? So these coefficients, which are, you could think, weights assigned to all these instanton sectors, they are determined by these small r's, which come from the expansion of this log, which is essentially a result of the quantization condition. So one of the things we see is that these coefficients are somewhat rigid. If I would, change some slight details of this potential without really changing the topology of the Stokes graph, the exact quantization conditions would not change. Therefore, the RKs would not change. Therefore, the UNMs would not change. But what would change is the perturbative fluctuation, the perturbative coefficients of our energy. And those are in here. So what you can see here is that I promised you an exact trend series, and it's exact in the sense that it now gives you all these weights expressed in terms of 2 perturbative quantities, which are this dual period and the energy. So you still need to compute those perturbative quantities, but once you have, say, 1,000 coefficients of those, now you can compute any saddle point expansion up to 1,000 coefficients. So that's your computational limit here, and it's this piece which is sensitive to, small changes in your potential. But these coefficients are fairly rigid. All right, so this is a picture of some coefficients. Again, you can see some ambiguities and some epsilon dependence. So here I've put them in a grid. So every row is an instanton sector. So you see every additional instanton sector gets an extra piece. But you can see that these pieces are parity dependent. So this is the famous level splitting, right? And you can also see that this checkboard pattern, you'll find the ambiguities. Note also that every imaginary piece is indeed ambiguous. And so the next part, what I want to show you is how we can do alien calculus to explain why these ambiguities appear and why everything is consistent. Do this. All right, so that will be the next part. So any questions so far? All right. So now we finally get to the resurgence, which is actually the most important part, of course. So, um, as um, as I maybe already told you, if not, this energy expansion is divergent. So if you look at the growth of these ENs, of course they depend on the parameter t, but regardless of what value you assign to t, you will find that these ENs grow double factorially. Let me and so, of course, as we want to try to turn these divergent series into sensible functions, we use Borel resummation, which starts with taking a Borel transform. I'll use the auxiliary variable s. I'll be a bit cavalier about the conventions for a Borel transform. I will, in this case, of course, divide now by 2n factorial, because this is the growing behavior. It's, of course, related to the fact that I picked my labeling in this particular way. And if you study the Borel plane, you will find that this Borel transform has singularities, and those singularities lie at multiples of A, and A is going to be the dual classical period. And this is already interesting because our transseries here, where was it, has powers in lambda, in square root powers of lambda, and these, of course, are 1/2 periods. So this already tells you something that is well known, and you can already see over there, is the fact that the perturbative energy misses out on the odd instanton sectors. Because if it would see the full transseries, you would expect also a singularity here and here and here, but they do not appear. So we're going to see in a second how this works. Naturally, you would like to turn this thing into a function. So you do the Borel summation. Yeah, I apologize for this bit. But what I like to do, because usually, of course, one picks in a contour either over or below, but what I would like to do is rewrite this in this particular way by changing the integration variable. And in this way, now the location of the Borel singularities starts depending on the value of h bar. And in particularly, it will depend on the phase of h bar. So remember that I told you that these quantization conditions were ambiguous, and those ambiguities, of course, you can see appear in the trend series, that we could relate these signs to the imaginary component of h bar. Here we can do the same thing with this resummation ambiguity. So if we pick this plus delta choice, we will find that S must be negative, or as a negative imaginary component. So those singularities will now move over here. So our natural resummation prescription becomes the S plus resummation, whereas in the minus delta case, we find that the singularities move up. And so our resummation prescription becomes S minus. Yeah, sir? The what, sorry? Um, yeah, I think this is what we're going to see in the end, that there's a trend series in the middle indeed. I think that's what I don't know the precise method you're mentioning, but I think I know what you mean. There are branch cuts. Yeah. 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 Yeah, I think so. We're going to see in a second this we're looking at two trend series, essentially with a trend series with a certain plus ambiguity and a minus sign, and there is some you can interpolate in between to find a median trend series whose median resummation produces the physical value. And probably what you mean is that there's a particular choice of paths which give you this trend series, right? Yeah. Yeah, okay. Yeah. I think we're gonna see something familiar in a second. Yeah. There will also be singularities at the negative axis. Yes. But we're doing for the physical picture that we're studying, these will not be relevant, uh, because we're assuming h bar to be real and positive, so we will only be concerned with singularities lying in a positive on the right side of the complex plane, and especially those on the real axis. But from a mathematical point of view, indeed, it's interesting to consider all singularities. And in this case, there will be singularities on the negative axis, yes. Also at multiples of a, but negative a. Yeah, exactly. Yeah. And this is essentially related to the Borel plane of the quantum period. E is simply the inverse of the quantum period. And in a second, we will derive its alien calculus using the quantum period. What do you want to change? The resummation contour or? If you take S to minus S, you say? I don't know. There's another, there is, so what you can do in the original trend series is you can take this T before quantizing it, and you can make that thing go move that clockwise around the origin, and then you'll find that there is some sort of SL to Z transformation on the trend series. But in the Borel plane, I don't know. We can we can discuss it. For this story now, I think the most important thing to note is that this gives us a natural resummation prescription for either trend series, because we could identify these two with two trend series corresponding to the two choices of ambiguity. So what this suggests is if I take the trend series with the plus delta, then this should correspond to the resummation of the trend series with the minus delta choice. And of course, as you know, if you know a bit of resurgence, you know that this can also be written in terms of a Stokes automorphism acting on this guy, and this should produce this guy. So that's what I now want to show you, how we can kind of demonstrate this. And to do that, we will revisit, or we'll use some results from Delabert, Dillinger, and Pham, who tell us how this quantum period jumps. So the quantum period that I'm going to study is this guy. So it's the original quantum period. Now we're back as E is a modulus. And what Delabert, Dillinger, and Pham show us is that this guy also has singularities along the positive real axis. This is the automorphism which relates one resummation to the other. And what we find is, again, the same object plus I h bar. So this is a bit unfortunate. Let's write it here. So this is also the quantum period again in E. So what I show you now is that this Stokes automorphism, which was given to us by Delabert, Dillinger, Pham, we can use that to derive the action of the Stokes automorphism acting on our energy. And what I want to do first is note that this automorphism can be expanded as a sum of alien derivatives. So if you want to know more about this, you can read all about it in Daniele's lecture notes. And essentially what these objects tell us, these alien derivatives, without going too much into detail, is they act on formal or on saddle point expansions, and they produce new new saddle point expansions. So in particular, this relation given by Delabert-Dillinger-Pham can now be written in terms of a action of an alien derivative, or pointed alien derivative. It's labeled by the location of a singularity. So for instance, delta 2a would be telling you how our Borel transform is related to the second saddle point here. And when we act with this thing on our quantum period, we find, let's see, is this readable? Sorry, I'm being a bit... So this is again the exponentiation of L over h bar, and here with the dual period with E. And what you can now do is, okay, so we know how these alien derivatives act on the quantum period, but we want to know how they act on their inverse. So on the energy trends here, of the energy, perturbative energy. And so what we're going to do for that is use a very nice trick, which I want to show you. Where can I make some space? Let's switch over here. And this trick I'm going to borrow from yet another paper from Delabert-Dillinger-Pham. And it's some sort of chain rule for alien calculus. And I like this trick very much. That's why I want to share it with you. Maybe all of you know it, but essentially what this, so what DDP write in this particular paper from '93 is that assume that you have some point alien derivative acting on a formal power series F, which depends on Z, and it too has an extra parameter in there, but that parameter now is also going to be a formal power series of Z. And then what we find is you can regard it as some sort of total derivative. We're going to write it now as the sum of two partial derivatives. So first it acts on F. So it works on the second argument. It's the partial derivative with respect to the second argument. But then we also get F differentiated with respect to G multiplied by this guy working on GZ. So this is a very nice trick, and we can use it for the following object, because we can take our energy expansion and we can replace T by its expansion. And this thing, of course, should be a number. This is a composition of a formal power series with its inverse. The inverse carries a parameter E. Let's call it E0. So this thing should be, again, the number E0. So if I act with this alien derivative, point alien derivative, at this composition of series, I should be acting with it on this guy, and this guy should be 0. But here we can now use the fact that this is a total derivative. We can decompose it in these two pieces. And then we can relate the resurgent structure of this guy to this guy. And what we find, I'm going to maybe skip one line in the interest of time. What we find is so in principle, okay, I'll write it out. In principle, we'll find this. Right? And now we can plug this result in here. Then we still have a relation between objects which is eventually depend on the modulus E, we can then plug in again the inverse function, so E of t, and then we find the result that this thing as an honest function of t is 1 over 2 pi I minus 1 to the L multiplied by, oh wait, I can just use lambda, right? Because lambda was, is it up here somewhere? Lambda was exactly our exponentiated dual period with respect to t. So I can derive this now also in a similar way for lambda, and you get a similar expression. Sorry, I made a mistake here. Being a bit sloppy. And here I find and now maybe I had it here already. So in this trend series, I'm gonna, the thing on the right hand side in the brackets, I'm gonna call E and M. These are these building blocks of our trend series. And then you can derive that this equation implies so when the L step alien derivative, point alien derivative, acts on this particular saddle point labeled by N and M, what we see is that we jump 2 rows and 1 column. All right, so I apologize for the somewhat dubious handwriting, but you can forget all about this stuff, and in the end, just think about this equation. This is, I would say, essentially result number 2, and even nicer, you can graphically depict it in this particular way. So now you can write out all these saddle points in a nice way, how all these saddle points are connected. And you can also see that many saddle points are not connected. So this is not a, what I would say, a fully resurgent trend series, because clearly there is many sectors don't see each other.
Can you think that there is a sort of like theta angle, so the blue and the red are different, we have also theta angle?
Yeah, it's a good point. So what we do in the paper, we redo this thing. So here you could think of the epsilon, right, being a topological sector. But you can see here already that at the 2 instanton level, you see 2 pieces which don't see each other. Now, it is true that in this case, the second piece actually scales secretly with epsilon squared. So you could think of that as your theta angle. But what we also did is this for the cosine potential, so periodic or the Mathieu equation. And there you find all sorts of, you find polynomials in cosine theta, where theta is the Bloch angle. And indeed, you can see that there is a separation of topological sectors. But the problem is that the separation is necessary, but it's not sufficient. So you will find sectors which have the same theta angle dependence, yet will be disconnected. I have some backup slides at the end. I can show you the same structure. But for now, you can see that clearly not everything is connected. But what you can do, I have not included it here, but you can now check with Mathematica notebook that these ambiguities here are indeed cancelled by these alien derivatives. So if you act with, say, the first delta on the perturbative energy here, you will get essentially a plus 1 over 2 pi I. And you can see that the E20, let's see, no, other way around, differs indeed by 1 over 2 pi I. So you can check by hand or with a Mathematica notebook that indeed all these ambiguities are a result and more or less cured by applying these alien derivatives. So the last thing I want to get into, I don't know how we're doing on time. let's say 3 more minutes, is show you that this thing actually, that there's some structure going on here. So let's look at this particular subset of the transseries. This thing is what we call a minimal resurgent transseries. It's an extension of this notion introduced by Guillemarino, which is a minimal resurgent structure, where essentially we include all the formal power series which resurge from a particular node, in this case the perturbative energy. So this is actually a closed structure. And if you look closely, you will see that this, for example, is also a closed structure. So what I want to show you is that you can understand why these structures appear if you look a bit longer at this delta t, which I am now erasing, unfortunately. It will take me 5 minutes, hopefully, and then I'm done. So if you look at the equation for delta t, which I wrote here, is that you find is that this thing can be decomposed into this piece. Plus this piece. And now if you look closely at this, so this seems to be some kind of happy accident, but it turns out you can do this also for the cosine potential and many more. What you see is that we have two contributions, actually. We have one piece which now has even powers of the instanton transponomial lambda, and which depends on the ambiguity and has imaginary pieces in there, but which does not depend on epsilon. And then there's a piece here which depends on epsilon, but is real and non-ambiguous. What you can see, what one can see now is if we put epsilon here to 0, which you formally cannot do, but let's cheat here a little bit, then you will be left with this delta t, which I call delta t min. I'm going to introduce sigma, which is going to turn out to be a transseries parameter. And it turns out now that if you take the energy, you can define a minimal transseries, which is the energy evaluated at t plus delta t min. And that's exactly this object here. So what you find that this is E plus our double sum, some new coefficients U tilde, which you can also explicitly compute, a sigma to the power m, I think plus 1, yeah, here. And then here you have your usual building blocks E and M. No, E2 and M, right? Because this now only has even instanton sectors. And you can check that the automorphism acting on this minimal transseries with sigma produces the same structure with now sigma shifted by 1 over 2 pi I. And the thing is, you can also shift the E1,0 sector in the same way, and it gives you transseries for this guy. In fact, every closed sub-transseries that you find in this full transseries can be written as simply that particular saddle point expansion and then the t shifted by this object. So this first piece generates the resurgent part of this transseries. It's the part which essentially has this transseries parameter baked into it, and the Stokes automorphism essentially shifts this parameter, which in this case is either plus or minus 1 over 4 pi I, by 1 over 2 pi I. And secondly, then you can ask, okay, so we have all these minimal transseries. Which ones should I include for the full transseries? Well, so here's another picture of that. Well, these are these nodes. And so these nodes are generated by this guy. So I can write down a similar definition for something that we call in the paper delta t med, median. This generates this particular trend series, and these nodes are all real, with the coefficients which are all real and unambiguous. And these pieces, this trend series you can median resum. As you can see, it is a trend series which essentially has sigma is 0. And you can imagine that, the median resummation, as you might know, can be written in this particular way or this particular way. So you can see that this half automorphism shifts sigma to either one side, and then you find, of course, that the resummation produces, again, the physical value. So a consistent picture kind of emerges, and this is the guy which, produces this collection of, you could think, highest weight states, which all give rise to their own minimal trend series extension. So this is what we mean by this idea that this full trend series seems to factorize, because all these minimal trend series have an identical structure in that sense. All right, I think that was all I wanted to tell you. So thank you very much. I'm afraid you lost me when you pulled up. Yeah, I cheated there. Yeah, so epsilon, so physically epsilon is indeed a parameter which should be plus or minus 1. So here with cheating, we're exchanging essentially epsilon just for a variable, and we say epsilon can now temporarily be anything. So by setting epsilon to 0, we're kind of zooming in on this particular sub-trend series. Of course, this is not the trend series. The true physical trend series is the whole thing. But this is just a mathematical trick to throw out most sectors and just keep these. So this is just a mathematical trick. In the end, if you want to compute the physical value, of course, epsilon going to be plus or minus 1. So this is not the physical trend series. This is just a mathematical trick. It's a no. It's a choice. Yeah. Yeah. Where you can. Yeah. Yeah, maybe. It's the thing is here, it's epsilon, right? It's plus or minus 1. If you do the same thing for the cosine, for the periodic potential, it will be the cosine of theta. And yeah, and there so I can, if you want, I can briefly show you that. So this is the splitting for the cosine potential. So here you see a similar structure. The details are a bit different. The first piece is again this has again the log, which is very resemblant of this Delabaert-Dillinger-Fam formula. Again, it has an ambiguous term in front. And now you see that the second piece again has this quantum number, which is now the cosine of theta. And here you can again generate the trend series coefficients. And these will now be polynomials in cosine theta. So this relates to what you said about these theta angles. So yeah, I use it as a trick, yeah, essentially. If you pick another potential. Yeah, it's a good question. So we did this for 3 potentials. So for the cubic potential, you only find this top term. So you get a fully minimal resurgent trend series. And I think the reason for that is because the cubic, essentially, it looks like this, right? And classically speaking, a solution which tunnels out must come back, and therefore you always get integer powers of the in this trend series. Whereas in a double well or any other, if you have more wells, you can also just go in odd times up and down. So if you go to this, so if you go to the double well or this cosine potential, then you find these square roots of lambda, so half integer dual periods. And so far, for these two models, it turns out you can factorize in this particular way. I would say that this at this point seems a happy accident, but I think there is. I think this would, yeah, I would put my money that it would be more generally applicable. We studied three potentials and it works for the three potentials. Yeah, it would be a natural extension to probe a few more and see if that also works. But I'm pretty confident that this structure is somewhat universal, at least for one-dimensional quantum mechanical oscillators with a polynomial potential. If you come up with potentials with, say, a singularity on the real axis, then things might change. But